Okay, so welcome back, everyone, to our new classroom. We're gonna play this by ear. I've never done this before. This is a new way of trying to do this. All right. Since we're not quite so strictly limited to classroom times, I'm probably going to break these videos up by sort of topical rather than necessarily trying to fit them exactly into our 75-minute lecture time. And so since we started a sort of a new topic a little bit at the end of lecture on Wednesday, I thought I would just restart that topic. So the first little bit of this will be stuff that we've already covered a little bit in class on Wednesday, but now we have a new starting point. So we're going to start in here on chapter 5 in our text, which begins the first couple of sections talking about the concept of free energy, both the Helmholtz free energy and the Gibbs free energy, what they are, ways that we can think about them, setting up where we're going to be going for the rest of chapter 5, which is using these concepts to examine various sort of chemistry style applications for classical thermodynamics. So let's start with the concept of enthalpy. All right, so the enthalpy, remember, is this quantity defined as the energy plus this term P times V. And again, this was the energy needed to create a thermodynamic system, to generate that thermodynamic system out of nothing. Obviously, you have to add the internal thermal energy, U, but you also have to add a little bit of energy here, PV, if you're working in an environment of constant pressure. You have to pay a little bit of extra energy to push open a gap in that constant pressure environment in order to insert your system into it. So the enthalpy would be the total energy required to generate this system at constant pressure. And vice versa, if you were to sort of wave your magic wand and cause that system to disappear, then you would spontaneously generate recover not only the internal thermal energy of the system, but also, again, this little bit PV, which was, that would be the energy released by the now hole in our constant pressure environment collapsing into, or back in, as the air sort of rushes back in. But if our system is thermally coupled to the environment that we bedded in, then some of the energy here that goes into the system could come from the environment in the form of the free transfer of thermal heat from the environment into our system. So if we wanted to account for instance, how much of the energy might come from a thermal environment, to begin with, if we ignore the pressure term, and we just want to know if we insert a thermal system into an environment, but we're going to pull some of the energy content for that thermal system from the environment, then we introduce this concept of the Helmholtz free energy, which we define as the internal energy U minus this term T times S, which represents, this is the energy available from the environment, which can go into the creation of our system. Or alternatively, if we destroy our system, then this amount of energy Ts must be lost to the environment as waste heat, which carries away the internal entropy of our system, right? So this T, this is the temperature of our system and its environment, and S is the internal entropy, the entropy of our system. And to annihilate our system, we have to get rid of the entropy, and therefore there's this amount of energy, Ts, would be lost upon annihilating our system. So it's a similar concept to enthalpy, where we're accounting for, again, in enthalpy, the effect of interacting with the sort of pressure environment of our system. And with the Helmholtz free energy, Helmholtz Fe, this accounts for interacting thermally with our environment. So the enthalpy is for interaction with the pressure environment. And the Helmholtz free energy is for interaction with the energy environment, basically. Or with the energy in the environment. And if we want to have our system interact both with the pressure of the environment and with the energy in the environment, then we need a third quantity, which is our Gibbs free energy, here defined as basically one that includes both the PV and the TS terms, so that you have internal energy minus temperature times the entropy plus the PV term. This is what we call the Gibbs free energy. And again, this is similar to the Helmholtz free energy or the enthalpy. And indeed, we can generate a little chart here where we have the internal thermal energy U, the Helmholtz free energy F, the enthalpy H, and the Gibbs free energy G. And if we want to get anywhere between these four thermodynamic potentials, going this way to the right on our chart means that we have to subtract a TS term, and going down on our chart means we need to add a PV term. And these four quantities, the energy, the Helmholtz free energy, the enthalpy, and the Gibbs free energy, these are what we call the thermodynamic potentials. And the reason for that is, we'll see here in the course of our discussion, that these very much act in the way or similar ways to how things like potential energy acts in a mechanical system. The first way in which these behave kind of like a potential energy is that for the most part, we're not interested in the total free energy of the system or the total enthalpy of the system, because for the most part, we aren't magicking our system up out of thin air, but in fact, we're making some sort of a change to our system or allowing our system to interact and undergo some sort of a change, and therefore what we're interested in is not so much the absolute value of these potentials, the total energy, the total Helmholtz free energy, the total enthalpy, and the total Gibbs free energy, but rather changes in energy, changes in enthalpy, changes in the Helmholtz or Gibbs free energies. These would be relevant calculations if, instead of just annihilating in sort of matter-antimatter explosions, but we were doing some less dramatic change to the system. So, for instance, if we had a process which was taking place at a constant temperature, but not necessarily at a constant pressure, then we would be interested in the change in the Helmholtz free energy, because here we are talking about, again, the temperature. We're going to account for the the energy available in the thermal environment from that could be transferred into or out of the system, but we're not going to say anything about the pressure environment. So our change in Gibbs free in the Helmholtz free energy would be our delta U minus T delta S. And our delta U, by the first law of thermodynamics, would be Q plus W, and again minus our T delta S term. If our process, whatever it is that our system is undergoing, isn't generating new entropy, then the Q term, the heat, would just be equal to T delta S, and our Helmholtz free energy here would be F, or delta F, is just equal to the work. So in other words, the work you did to the system would be the only thing that changed our Gibbs free energy, because our delta F here, the Q and the T delta S terms, would cancel one another. However, if there is some sort of entropy generated during our system, so that the total T delta S term would be larger than the Q term, such that, so this over here, this would be no new entropy. But if there is new entropy generated in our process, then Q minus T delta S will be less than 0, and our change in the Helmholtz free energy then would be less than the amount of work that we could generate. And so in total, at best, the Helmholtz free energy is the work that we could get out of our system, or by whatever process we were putting into it. This is, again, for a constant temperature environment, but not one where we have said anything about the pressure. If we wanted to work on a process which was at both constant pressure and in thermal contact with its environment. So we had process at constant pressure, where we don't really care about the work being done to generate space in our environment. We just care about how much energy is this chemical reaction going to produce in some sort of usable form that isn't about or dealing with the pressure changes or the volume changes of our system. Then we'd want to use our Gibbs free energy. And again, we could change or write this down as the change in the Gibbs free energy is again equal to our change in energy minus T delta S, but now plus also the P delta V term. Again, using the first law of thermodynamics to replace delta U with Q plus W minus T delta S plus P delta V. And again, like we saw with the Helmholtz free energy, at best, Q minus T delta S will be 0, and will be less than 0 otherwise. And the total work here would be the P delta V term needed to account for changes in the volume, plus other forms of work. And if what we actually care about is the other forms of work, then the Gibbs free energy would be representative of, at maximum, the other work that went into our system, again, at constant temperature and pressure. So, in other words, the way we could think about both the Gibbs free energy and the Helmholtz free energy is these represent the available energy that our system has for doing work in some sort of meaningful way, other than, making space for itself as the volume of our system changes or whatever during during some sort of process or reaction. So again, the Helmholtz free energy is relevant mostly for when either you want to account explicitly for volume changes in terms of the energy, or much more likely, you don't really care about the volume changes, or the volume change is going to be small, so you might have a system where you're talking about electrical energy inside of a solid battery or something like that, where the volume change isn't going to be a big deal. Then you might go ahead and use the Helmholtz free energy. In many cases, for chemistry kinds of experiments, the Gibbs free energy is sort of your go-to choice. Let's use an example, or look at an example of using the Gibbs free energy. In this case, in the context of the electrolysis of water. So, for instance, here the chemical reaction we could write as H2O goes to H2 plus 1/2 O2. So if we have a mole of water that we place a couple of electrodes in and pass electrical energy into the water system, we can generate a mole of hydrogen gas H2 and 1/2 a mole of oxygen gas O2. So 1 mole of water goes to 1 mole of H2 and half a mole of O2. If we go to the back of the book and we look at the liquid H2O, part of the reference data chart, the thermodynamic properties of selected substances, that's on page 404 in my text, 404 and 405, but this is the chart that we've been using throughout the semester. And if you look at liquid H2O, that's the H2O with an L behind it, and we look at, for instance, the Gibbs free energy of 1 mole of water, actually, let's look at the enthalpy of 1 mole of water. So the change in enthalpy here is 286 kilojoules. And of that 286 kilojoules, when we looked at this before, we said that the PDV term, so the pressure term in that 286 kilojoules, that was 4 kilojoules. So of the 286 kilojoules, 4 kilojoules represents the making enough space in our constant pressure environment to include the much larger gaseous portions from our otherwise very compact liquid portions. But the remaining 282 kilojoules of energy would have to come otherwise into the system. But we might ask ourselves, how much of that 282 kilojoules of energy could we pull from the energy, or the temperature of our environment, from the ambient thermal energy of the environment, and how much of it would we have to come from our electrical source? Well, the entropy of a mole of H2O is 70 joules per Kelvin, and the entropy of a mole of hydrogen is 131 joules per Kelvin. The entropy of a mole of O2 is 205 joules per Kelvin. So the total change in entropy for this reaction is going to be the change in our, the entropy of the hydrogen, a mole of hydrogen, so that's going to be our 131 joules per Kelvin, plus half of the entropy of a mole of oxygen. So 1/2 times 205 joules per Kelvin. So that's the final entropy, and the initial entropy we started with was the entropy of a mole of water, so minus 70 joules per Kelvin. And this gives us a delta S of 163 joules per Kelvin. So running this process generates 163 joules per Kelvin of entropy in going from liquid water to hydrogen gas and oxygen gas. By generating that entropy, or if we pull that amount of entropy out of the thermal environment, that entropy that was generated could come and bring heat with it. So the heat that can enter is just going to be T delta S, and if we're at room temperature, that'd be 298 Kelvin times 163 joules per Kelvin, and that gives us 49 kilojoules of energy that we could pull out of the environment. So again, if we look at the change in the enthalpy here, that's the change in the energy plus P delta V. The change in the energy, that had to be 282 kilojoules. And again, the PDV term, that was our 4 kilojoules. And that gave us our total 286 kilojoules of enthalpy. If we want to look at the change in the Gibbs free energy, that's again our delta U plus P delta V minus T delta S. So now we're allowing some of the heat from our environment to enter the system. We've got the same 282 kilojoules of energy that needs to be added. 4 kilojoules of plus we have 4 kilojoules of the changing volume term, and our 49 kilojoules available as ambient heat, then the amount of free energy that we would need to supply from our electrical system running the electrolysis would be 237 kilojoules. So to split water into hydrogen and oxygen, we need to supply the 237 kilojoules of electrical work per mole, and we can suck 49 kilojoules of energy out of the environment at room temperature, and this will give us the required 286 kilojoules to generate our to run the reaction forward. Okay, let's while we're talking about free energies and enthalpies and these other thermodynamic identities or thermodynamic potentials, let's revisit the thermodynamic identity, which, remember, we defined or we described as this equation, du equals T ds minus P dV plus chemical potential mu dN. Let's look at what happens to the thermodynamic identity when we write it in terms of these other thermodynamic potentials. So let's start here with the enthalpy. H equals U plus PV, and differentiating this, we see that dH then is equal to du plus P dV plus V dP. That second one being what happens when you take the product rule and differentiate it. Well, du we could use we could replace this du with the original thermodynamic identity, and that would say that dH is du, which is T ds minus P dV plus mu dN. That's du, but also plus P dV and plus V dP. We can see here that the P dV terms cancel, and this gives us a new thermodynamic identity. The change in enthalpy dH is T ds plus V dP plus mu dN. Similarly, we could define, if we look at the Helmholtz free energy, F equals U minus T S. Differentiate this, dF equals du minus T ds and minus S dt. Again, we get two terms out of the second term because of the product rule for derivatives. And again, we can replace du with the thermodynamic identity. So that's T ds minus P dV plus mu dn. That's du minus T ds minus S dt. The TDS terms cancel, and we're left with a thermodynamic identity for the Helmholtz free energy, which says that dF equals minus S dt minus P dV plus mu dn. From this, we could derive new partial differential definitions or relationships. For instance, we could say that the entropy is minus dF dt if we're holding volume and number constant, and that the pressure from this term is minus dF dV, holding the temperature and number constant, and similarly that the chemical potential is dF dN, holding the temperature and volume constant. We could continue this game with the Gibbs free energy. G equals U minus TS minus or plus PV. And again, differentiating then gives us dg equals du minus TdS minus S dt plus P dV and plus V dP. And again, as we did before, substitute in the thermodynamic identity for this first du term. So T ds minus P dV plus mu dn minus T ds minus S dt plus P dV and plus V dP. The PdV terms cancel, the TdS terms cancel, and we're left with a thermodynamic identity for the Gibbs free energy, which is minus S dt plus V dP and plus mu dn. And again, this gives us new relationships between the various thermodynamic quantities, that the entropy could be written as minus dg dt for constant pressure and number, that the volume could be written as dg dP for constant temperature and number, and that the chemical potential could be written as dg dN for constant temperature and pressure. These in turn could be useful for converting values of the Gibbs free energy from standardized tables to non-standard temperatures and pressures and so on. So for example, if we look at graphite and go to the chart, the table at the back of the book, and look up carbon and graphite form, we find that the volume of 1 mole of graphite is 5.3 cubic centimeters. .3 cubic centimeters, which if we convert that to cubic meters, that's 5.3 times 10 to the minus 6 cubic meters. Well, if we take this middle relationship here, that the volume is equal to dg dp at constant temperature and number, and we want to know, well, we could look up the Gibbs free energy at, for instance, standard pressure. But if we wanted to know what happened if we changed the pressure by, say, a Pascal, then we could rewrite this equation here that says that the change in the Gibbs free energy, well, that's going to be the volume times the change in the pressure. If our change in the pressure is, say, 1 Pascal, or 1 Newton per square meter, and our volume here is 5.3 times 10 to the minus 6 cubic meters, then our change in the Gibbs free energy is going to be our volume 5.3 times 10 to the minus 6 cubic meters times our pressure change of 1 Newton per meter squared, and this gives us 5.3 times 10 to the minus 6 meters cubed times newtons per meter squared, or Newton meters, or in other words, 5.3 times 10 to the minus 6 joules would be the change in the Gibbs free energy of graphite if we were taking into account a change in pressure of 1 Pascal. All right, let's look at one other aspect of free energy, a different way to think about the Gibbs free energy and the Helmholtz free energy. We just talked about them as essentially the energy available out of a chemical process, or the energy required to be added to a chemical process, depending on whether it's exothermic or endothermic, in order for that process to run, or the energy that could come out of that process. In the Helmholtz free energy case, if we were just taking into account the thermal energy in the environment, and the Gibbs free energy case, if we're also going to take into account the sort of pressure environment as well. What we're going to talk about now is a different way to think about them, where we're going to think about how the system is interacting in its environment from sort of what's driving the system towards thermal equilibrium. Right, so an isolated system, what we said is that the entropy wants to increase as our system evolves towards equilibrium. It wants to maximize the entropy. That's for an isolated system, but in our case, now we're going to let our system be in thermal contact with some very large environment. And we're going to treat the environment as so large that it's basically a giant reservoir of energy or a giant reservoir of pressure energy, so that it can absorb changes in volume and it can absorb changes in energy without itself having much change to its pressure or its temperature. So in other words, we're going to treat this as a giant reservoir of whatever the relevant thermodynamic quantities are going to be. Again, the total behavior of this combination of the system and its environment is driven by the increase in entropy. So in other words, the system and environment will behave in such a way that the total entropy of the universe always wants to increase. And we could write the total entropy of the universe here as, or the change in the total entropy of the universe as the change ds total, and that's going to be the change in the entropy of our system plus the change in the entropy of our reservoir. All right, so this is the changing entropy of the environment, whereas this is the changing entropy of the system. All right, so if we go back to the thermodynamic identity, du is equal to T ds minus P dV plus mu dN. We can rewrite thermodynamic identity in terms of the change in the entropy. So ds here is 1 over T times du plus P over T times dV and minus mu over T times dN. And if we're going to let our system only exchange exchange energy with the environment, but not exchange volume or particles, so we can exchange the energy, but we can't exchange volume or numbers. So in other words, V and N are held fixed. Well, the change then in the reservoir entropy will just be, well, there's not going to be a dV term and there's not going to be a dN term. There'll just be this du term. So that's going to be 1 over the temperature of our reservoir times dur. And so the total entropy change will be ds, the change of entropy of our system, plus 1 over Tr dur. Well, any energy that enters our environment must have come out of our system, and so dur must be minus du. And if our system and our environment are in thermal equilibrium, then their temperatures will be the same. And so we could rewrite ds total is equal to ds minus 1 over T du, where now all of these terms are relating to the system, the temperature of the system, the energy of the system, and the entropy of the system. And indeed, we can rewrite this as minus 1 over T times du minus T ds. And that's the total, is change in the total entropy of the universe can be written in terms of just description of our system. Well, this du minus TdS, that's just equal to our dF, and so ds total is just equal to minus 1 over T times dF. So again, we've written the change in entropy of the entire universe in terms of the change in the Helmholtz free energy of our system and the temperature of our system. So now, instead of having to calculate the total entropy of the universe and make sure that's increasing, if we want this to be a positive number, then we just have to make sure the thing on the right is a positive number. And the only thing that we need to do that to make sure the thing on the right is a positive number is to make sure that dF is a negative number. So ds total will be positive if dF is negative. In other words, total entropy of the universe will increase if the Helmholtz free energy of our system decreases. So now we can replace thinking about entropy entirely. We don't have to think about the rest of the universe. All we have to know is that our system is going to behave in such a way that it wants to decrease its Helmholtz free energy, and indeed that the thermal or the equilibrium condition will be that condition where the Helmholtz free energy is minimized. So we've replaced maximize the energy of the universe with minimize the Helmholtz free energy of our system. So this gives us a way to think about the likely behavior of our system when in contact with a much larger environment without having to think about the environment. All we have to do is think about the system, and this allows us to predict the behavior of our system. So if we were just allowing the system to exchange energy, then the behavior would be that we wanted to minimize the Helmholtz free energy, or have the Helmholtz free energy always decrease if we were exchanging energy with our environment at constant temperature. What if we allow the volume and energy to exchange in the environment at constant temperature and constant pressure? Then we could do a similar game here. Again, the change in entropy of our reservoir then would be 1 over temperature of our reservoir times the change in the energy of our reservoir plus pressure of our reservoir divided by the temperature of our reservoir times the change in the volume of the reservoir. As before, any energy entering the reservoir must have come from our system, and any volume gained by the reservoir must be volume lost by our system, and the temperature of the reservoir is the temperature of our system, the pressure of the reservoir is the pressure of our system if our system is in temperature and pressure equilibrium with its environment. So predicting the behavior of the system, again, we would have to go back and look at the total entropy, which we could write as ds, and replace the du and dv terms with their counterparts here in the system. So minus 1 over t du of the system and minus p over t dv. And again, we could rewrite this as minus 1 over t times du minus t ds plus p dv, where now again we've written the total entropy change of the universe in terms of only changes in our system, and as you might guess, this du minus tds plus pdv, that's our change in the Gibbs free energy. And again, if we want ds total to be a positive number, in other words, that the entropy of the universe increases, all that we need to require is that the Gibbs free energy of our system decrease. So again, we can forget the reservoir itself, and the behavior of our system will be in such a way that the Gibbs free energy of the system tends to decrease. And we could summarize sort of the behavior of the system, which system under various conditions, so at constant energy and volume, All right, so at constant U and V, entropy of our system will increase, but at constant temperature and volume, the Helmholtz free energy will decrease, and at constant temperature and pressure, the Gibbs free energy of our system will decrease. Here we can now finally see why we call these things thermodynamic potentials, because in this case, the natural behavior of the system, the way the system wants to behave, is such that the free energies will decrease under these various conditions in much the same way that the natural behavior of a mechanical system is to have its potential energy spontaneously turned into kinetic energies and things like that. In other words, the potential energies want to decrease. The natural behavior of a mechanical system is to run towards lower potential, and indeed a mechanical system will reach a stable equilibrium at a local minimum in the potential. Similarly, our thermodynamic system will reach a local equilibrium when we minimize the free energy. Let's take a pause for a moment and introduce another concept. We've got a whole bunch of thermodynamic variables that we've talked about so far that are now sort of floating around. There's the thermal energy U, the volume of our system V, the number of particles in our system N, the total entropy of our system S, the temperature of our system T, the pressure of our system P, the chemical potential of our system of particles mu, the enthalpy of our system, the Helmholtz free energy of our system, the Gibbs free energy of our system. There's a whole bunch of different quantities. But imagine what would happen if we took our system and made a copy of it and stuck it right next door, and assume that those are in fact identical and not awkwardly drawn as I've just drawn them. So that we've taken the system, magically copied every piece of that system and plunked it down right next door. Imagine what that does to these various quantities. And we're going to sort these quantities into two types. If a variable doubles under this process, then we call that an extensive variable. But if the variable stays the same, then we call that an intensive variable. And an extensive and an intensive variable, the distinction here is that extensive variables scale with the size of the system, right? So imagine that you made a copy of the system. Let's think about the first one here. Is the total thermal energy of the system, is that an extensive property or an intensive property? Well, if we double the amount of system, then we're going to have an energy U over here and an energy U over here, so we will indeed double the energy of the system. So that's an extensive variable. And similarly, we would double the volume, we'd double the number of particles, we'd double the entropy, we'd double the Helmholtz free energy, or the enthalpy and the Helmholtz free energy and the Gibbs free energy. So all of those, the volume, the number of particles, the entropy, the enthalpy, the Helmholtz free energy, and the Gibbs free energy. These are all extensive. But if we doubled the system, the temperature is T over here, but the temperature is also T over there. It's not like the system has doubled its temperature. Indeed, the temperature of the system hasn't changed. So temperature is an intensive variable, and similarly, pressure and chemical potential, they tend to be intensive variables of the system. Doubling the system like that, making a copy of it, wouldn't change those. What about the total mass? Well, that would obviously be an extensive variable, but the density would be the same before and after doubling the system. So these intensive properties, these tend to be descriptive properties of pieces of the system, right? Or average behaviors of pieces of the system. The temperature is something like the average energy per something, per particle, per moving part, etc. of the system. The pressure talks about is an average aggregate behavior of the system. Similarly, the chemical potential and the density. These are aggregate descriptions of the system, whereas the stuff up here, energy, volume, number of particles, entropy, etc., these tend to be quantities, large chunks of stuff contained within the system rather than descriptive properties of the system. So the difference between extensive and intensive variables is related to this concept of what happens to the system. Similarly, for instance, if you want to think about it in terms of sort of geopolitical concepts, GDP, gross domestic product, that's an extensive variable. If you had twice as many United States, they would generate twice as much GDP, but the per capita GDP, that's an intensive variable. That describes per person what's the relative generation of stuff in the United States. So per capita kinds of things, those are the intensive variables, whereas gross products, those are the extensive variables. The amount of stuff, that's going to be an extensive variable. The quality of that stuff, that's going to be an intensive variable. And there's a certain logic to the math of how these things. If you take an extensive variable and multiply it by an intensive variable, then what you get is another extensive variable. So for instance, volume times density gives you mass. Right? Mass is an extensive variable, volume is an extensive variable, density was an intensive variable, but if you multiply a density by a volume, what you get is a mass. If you multiply an extensive property by an extensive property, say volume times number of particles, very likely you've done something wrong, because that isn't either extensive or intensive, it's a mess. So if you find yourself multiplying two extensive variables together, probably there's not a good reason for doing that. If you're adding extensive variables together, then that's just fine. For instance, the enthalpy, we said, is the energy plus P times V. Well, energy, that's an extensive variable. Pressure, that's an internal intensive variable, but volume is an extensive variable. And so pressure times volume is an extensive variable. So everything over here on the right is an extensive variable, and what we get over on the left, the enthalpy is also an extensive variable. But if we try to do something like the Gibbs free energy plus the chemical potential, that really doesn't make a lot of sense. That's an extensive variable, the Gibbs free energy, plus the intensive variable of the chemical potential. And if you doubled your system, you would double the Gibbs free energy. You wouldn't change the chemical potential, and this G plus mu, again, is probably not a physically meaningful quantity. Why are we talking about extensive and intensive variables? Well, because it sort of falls into what we're going to discuss here, which is a relationship that we can derive between the Gibbs free energy and the chemical potential in the context, and that is, remember earlier we had been looking at different versions of the thermodynamic identity in terms of these other thermodynamic excuse me, these other thermodynamic variables or thermodynamic potentials, and in particular we had this relationship here between the volume and the Gibbs free energy. So we can say here, or not volume, but not the volume in the Gibbs free energy, but this relationship here between the chemical potential and the Gibbs free energy. So the chemical potential here we could write again as dG dN, holding the temperature and pressure constant. Now, one thing to notice about this equation, which is different from the other two relationships we got there, is that the two quantities that we're holding constant here are both intensive properties of our system, the temperature and the pressure, neither of which scale with the size of the system. And that will turn out here to be important. So what this equation means is that if we add a particle to our system at fixed temperature and pressure, the Gibbs free energy is increased by an amount mu. And if we keep adding particles to the system, for each particle we add an amount of energy to the Gibbs free energy of mu. And no matter how many times we do that, because we're keeping the temperature and pressure of our system constant, the chemical potential isn't changing. So we could do this forever, and the chemical potential wouldn't change. The total Gibbs free energy then would just be proportional to the number of particles. It's going to expand and contract proportionally to the number of particles. And indeed, we could start from 0, add 1 particle, and then we would have a chemical potential of mu. And if we added 2 particles, we would have a chemical potential of 2 mu, and so on, so that we could write the total Gibbs free energy as just the number of particles times the chemical potential. Again, Gibbs free energy is an extensive property. It must grow proportional to this other extensive property, the number of particles in our system, and the constant of proportionality there is this constant mu, the chemical potential. Notice that this isn't true if we replaced the Gibbs free energy with the Helmholtz free energy. So there is a relationship between chemical potential and Helmholtz free energy, which is that the chemical potential is the Helmholtz free energy, or the derivative of the Helmholtz free energy with respect to number of particles, holding the temperature and the volume constant. So again, if we added 1 particle to our system at constant temperature and volume, we would increase the Helmholtz free energy by an amount F. But if we're holding the system at constant volume, then the density of the system has changed because the number of particles has increased, even though because the volume was the same, but we have more particles. So the density of the system has changed, and that means that the chemical potential of the system could be changing, and likely is. So we can't do this business of continuing to add an arbitrary number of particles to the system and always getting the same chemical potential change in our free energy, because we're holding constant an extensive property of the system, which means that all the intensive properties of the system are probably changing while we're doing that. Whereas here with the Gibbs free energy, we were only holding intensive properties of the system constant while changing an extensive property of the system, the number of particles. And thus, this relationship is true for the Gibbs free energy, but there is no correspondingly true relationship for the Helmholtz free energy. Well, this relationship in turn can be useful for thinking about the behavior of the chemical potential in the context, for instance, of an ideal gas. So, if we start with this relationship, the Gibbs free energy equals N times the number, or the chemical potential, I'll rewrite this for the chemical potential then is the Gibbs free energy divided by the number of particles. And we ask what happens if we differentiate or take the partial derivative of the chemical potential with respect to pressure. Well, if we're taking a partial derivative with respect to pressure, that means that the number of particles must be being held constant, because that's what this partial differential means. And so we don't have to apply the product rule here. We just have 1 over n times dg dp. And if we go back to our relationships for dg, we can say that dg dp, well, that's the volume. Right, so dg dp, holding the temperature, and again the number of particles constant, that's the volume. That was from our thermodynamic identity for the Gibbs free energy. And so we can then continue our analysis here that d mu dp is 1 over n times our volume, or in other words, V over N. Well, for an ideal gas, PV is equal to NKT, so V over N is going to be KT divided by P. And so d mu dp is going to be KT over P. And now we can do a separation of variables, d mu on the left, and K equals KT times dP over P on the right, and integrate both sides. dP over P. On the pressure side, we're going to integrate that from some fiducial or reference pressure to some arbitrary pressure. So P naught is a reference pressure, say 1 atmosphere, and P is our non-reference pressure. That's the pressure that we want to compare something with. And on the right, what we're going to have to look at is the chemical potential in our initial condition and the chemical potential at our final condition. So in other words, the limits of integration over here are going to be from temperature and initial pressure or reference pressure to up here, temperature and our final pressure. So on the left, this becomes the chemical potential at our final conditions, temperature and pressure P, minus the chemical potential at our initial conditions, in other words, temperature and our reference pressure. And on the right, we've got kT times the logarithm of P minus the logarithm of our reference pressure, or in other words, or kT times the logarithm of P over our reference pressure, P0. And if we rewrite this, we can write it as our chemical potential at arbitrary temperature and pressure, or our temperature and arbitrary pressure, is equal to mu naught at T, where this is the chemical potential at our reference pressure, plus kT logarithm of the ratio of pressures. So this is the chemical potential as a function of pressure, or equivalently the chemical potential as a function of density. We've derived this relationship for an ideal gas from our relationship here between the Gibbs free energy and the number of particles and the chemical potential. This allows us to adjust our chemical potential or think about the effects on the chemical potential of changing the density of our system, or equivalently changing the pressure of our system. If we had a gas made of multiple different chemical species, then we would have a version of this where we could talk about the change in the chemical potential of each of those species independently, because in the ideal gas limits, basically, because the particles aren't interacting with themselves, they're also not interacting with other species of chemical, then this relationship would hold independently for each of the chemical species in our gas, where we would have to then replace the pressures here with the partial pressure for that particular chemical species. All right, from here on, we're going to start investigating these concepts in the context of various chemical processes, and we'll start with that in the next lecture session.